Ready? Share screen. Algebra for noobs. And new file. Slideshow. Awesome. And then let me make cool. Okay. So thanks for joining us. Today, we're presenting the very important topic of algebra for noobs. More specifically, we have Dr. Jean-Éric Pin coming in a week, and he's going to present the super cool open problem that he's been spending a lot of time for decades trying to solve. And in order for us to understand that open problem, we need to have an understanding of a list of topics that he provided me over email, which is what we're going over today. So this presentation might seem a little scattered, and that's because not all the topics directly relate to each other, but most of them do. So it should be okay. So if you have any questions about a topic, you should just immediately ask instead of waiting to the end, and we'll do our best to address them. And with that,
I'll do the first interruption, following up with your rule. It's tomorrow, Dr. Ping, not next week.
No. Oh, it's next week on Friday. Tomorrow's Cheng.
Okay, great.
Yeah, so tomorrow Cheng is doing selected topics in cleaning algebra. And Cheng is a PhD student, theoretical CS at BU. And then on Friday of next week around noon, so in the middle of the day, because he's in Paris, Dr. Pin's going to do Generalized Star Height Problem.
Okay, great. Thanks.
Awesome. Okay, so here's the table of contents. So first, we're going to talk about first order logic, which I think everybody here already knows, but we'll just kind of familiarize ourselves with some of the terms for things that we're already kind of aware of, but don't maybe know what they're called. Then we'll go over monoids, and then words and languages. Then we'll just talk about finite automata and deterministic ones very briefly. We're not going to go into much detail. We'll go over regexes, which bizarrely Dr. Pin calls rational languages, but everybody else calls them regular languages. I don't know, maybe everyone else calls them rational, but I've never encountered that. Then we'll talk about metric spaces very briefly, like literally just what is a metric and what is a metric space. And we'll talk about the completion of a metric, and I'll give a couple examples. And then finally, we'll have like one slide on postfix notation, because Dr. Pin writes down functions in a slightly different way than most of us do, and maybe a better way, but it's a little hard if you're not accustomed to it. And then once you understand it, it totally makes sense. Okay, so in first order logic, we have two kinds of things that we need to deal with, namely terms and formulae. So terms are the atoms of our language. They are, and the stuff we make out of those atoms, and they are the universe of discourse. And we're going to manipulate terms to build our formulae, which are kind of the substance of our actual reasoning. Within terms, we have variables, and these are I think without lots of generality, Boolean variables, and it's reasonable to say that you have countably infinitely many variables. And we could call these whatever we want, but it's convenient to say like x0, x1, etc. And we have functions which map from variables to variables. I believe, interrupt me if anybody disagrees with me about that assertion. And examples would be like the POW function, which would like raise the first number to the power that is the second number, or the successor function, which adds one.
Functions would be mapping from sets of variables to
right, because you can have many to one.
Right.
You have many
yes.
to one.
Yeah.
And
point.
why is it going to variables? What is z here?
Literally just the output of the function, like how the successor function in this case returns another number.
So in case of s, it's integers, but it doesn't have to be.
Right.
Okay.
Yeah. Right. Like you could imagine a function that maps from, say, the space of 4 variable vectors to the space of 6 variable vectors, right? That'd be perfectly reasonable. Okay. Anki, do you agree with that formulation?
Okay. What did you say the range was? I mean, it maps a set of variables to what?
Well, I think you can construct different things. So we could allow like any arbitrary Cartesian product over variable space. So you could have like, matrices of variables or rows of variables. But I don't know that that gives you any more power than just saying you only get one variable back or one assignment back, right? Because, for instance, if I want to talk about, for instance, something that outputs a vector, I could just output the elements one by one. I would get the same result. But maybe I'm wrong. I'm not sure. Do you think
maybe we can say that functions map sets of variables to terms. So this will be a recursive definition.
Okay, I like that. That's what we're going to say. That's very good. So we're going to say the functions take as input one or more variables, but it's part of the signature of the function how many it takes. So you could have a 1-array function, a 7-array function, whatever, and the output is a term. I think that's a good definition.
Yeah.
Awesome. Thanks. Okay, on the other side, we have formulae, and formulae are things that are true or false. And an example would be that we can say that two terms are equal. In this particular example, I just said that two variables are equal, but we could have more elaborate terms, like a function on a function on a function on some variables or something. We have predicates. So predicates assign truthhood to kind of a statement over some specific variables. So an example would be Jacob believes, and then you could give different beliefs like Max is smart or Max is dumb, and the Jacob believes predicate might hold on some of them and not on others. We have connectives like not, which is a unary operator, and, which is a binary, is that the right word, operator, and or, which is similar to and. I don't know if you would really call negation a connective, but it's definitely an operator. So I guess when I say connectives, I'm also referring to operators here. And we have quantifiers, and I am only listing one quantifier because I already said negation, and we all know that for all is just not exists not. So we can say there exists some x such that Jacob believes x, or we could also say there does not exist some x such that it is not the case that Jacob believes x, and those would be equivalent statements.
And I'm the first one. It's nice to believe.
Okay. And our first two types of things, equality and predicates, convert terms to formulae, which is plural of formula. And our second two connect formulae. So that's sort of a philosophical difference between them. So what we can do with first order logic is we can reason about formulae, which kind of recursively means we can reason about the universe of discourse, namely our variables and predicates over them. What we cannot do is reason about, sorry, I just said the wrong thing. We can reason about terms, right? So we can reason about functions and variables, but we cannot reason about formulae. So I cannot say something in first order logic like there exists a sentence which is true if and only if all the other sentences are false or something like that. Like I can't enumerate over or quantify over the space of all logical sentences, which you can do in higher orders of logic. So that's an important difference. Okay, so we've covered all of the stuff I think we need to cover for first order logic, because Dr. Pin didn't say anything other than just cover the definition of first order logic. We're now going to move swiftly on to monoids. So a monoid has 3 ingredients. And I should say in all the algebraic content in this talk, I'm using the representation that Dr. Pin uses in this book. So if it looks weird to you, it's because Dr. Pin maybe writes it down differently. I don't really know what the standard is. So actually, you should point that out if something looks weird, because I think that's interesting. The first ingredient of a monoid is a set. In this case, I wrote M. Second ingredient is an operator, and it needs to be associative, which means we can move the parentheses around and it is still equal. And the third is an identity element. So I wrote 1, but the point is there's some element inside M, inside the set M, which when multiplied by other elements does not change them. So the smallest monoid is the set containing only the number 1 with any definition you could possibly come up with of the operator. There's really only one definition you could, which is that it does nothing, right? So if you have these 3 ingredients, we call it a monoid. And the free monoid over a set A is denoted A star. And it is the monoid where the operator is concatenation, like symbol concatenation. And the 1 or the identity is the empty string. So A star, an example would be if A contains the letters X, Y, and Z, then A star would have things like X, X, Y, Y, ZX, 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 but it would not contain the infinite string that is X, Y, X, Y, X, Y forever. So it's only finite concatenations of symbols. And importantly, it also contains the empty string, which is 1. One thing we can do with monoids is we can move from one monoid to another using a special type of function called a morphism, which I'm about to explain. A morphism takes as input stuff in one monoid and returns stuff in another monoid, and has to satisfy two properties. The first property is that it takes the identity of the first monoid to the identity of the second monoid. So in this case, 1 is n, and E is the identity in n, and 1 goes to E. The second and only other property is that it preserves multiplication. So x times y gets mapped to the same thing as the result of mapping from x multiplied by the result of mapping to y, right? X goes to j, y goes to k, x, y goes to jk. And this has to be true for everything.
You might want to clearly specify what the multiplications are. So on the left hand side, the multiplication is star within
Oh
x
yeah,
and y,
actually,
and on
that's a typo, right? Right here, it should say at.
Yeah, that should be at.
Ooh, good one. Okay. Let's go ahead and fix it. Fantastic. Okay.
Also, you could make that clear in the formula. Phi x star y equal to phi x at phi y.
Yeah, you're totally right. Thank you. Okay. I'm not going to fix the green box right now, but I'll fix it later. Fantastic. Okay, great point. So yeah, so the multiplication is different in each monoid, but the relationship is preserved by the morphism.
Now, one quick question about this too. So I think we don't have enough elements to and we have associativity, so it might not matter too much. So I'm assuming you can't say map X to E, right? It has to be 1 to E because E is the identity and 1 is the identity. But could you say instead of X to J and Y to K, for example, swap them and do X to K and Y to J? Would that provide a valid morphism, or is there something wrong with that?
In this case, that would work. But also, actually, you could make everything go to E if you wanted to, and that would satisfy all the properties.
So that would still be a monoid.
Yeah,
but
it would just be like a really trivial one.
But there are ways where I might have to be careful with J and K. If I mix those up, it could break something somehow.
Well, like you can't have 1 go to J, but you could easily make X go to, you could swap the relationship with X and Y. The problem would be if we had like a third element L, and then you made X go to L, but X, Y still went to JK, that would be the problem.
Okay, so in this case, we don't have to worry about it, but for more complicated systems, we might have to be careful with things besides the identity mapping.
Yeah,
okay,
right.
Great.
Yeah, because it has to preserve the multiplication. Some of you, and I'll have to make Ankit's changes on this slide too, but some of you might be familiar with the idea of a monoid homomorphism. And that is the same as what we mean when we say a morphism. And I'm informed by my friends in PL that the reason that we say morphism is because we are being category theorists. And the reason we say monoid homomorphism is because we're being algebraists, but I am really only a charlatan, so I don't know. But regardless, if you say either of those things, we will know what you mean.
You can also do the one object category. You can also mention that.
Okay. So you're saying that we could call something the one object category instead of calling it a morphism?
No, you can say a monoid is a one object category. So the morphisms are the elements of M, and then now you're doing a functor between them.
Oh, that makes sense. Cool.
Yeah, monoid can be implemented in category theory as a single element monoid, as a single element category which has multiple morphisms
multiple
from itself to
morphisms.
itself.
Yeah.
Gotcha. Okay, cool. Very cool. That's everything we need to know about monoids for at least what Dr. Pin asked me to cover. Now we're going to talk about words and languages. So an alphabet is a non-empty finite set. This is not a universal statement about all of math. I've seen multiple definitions of alphabet, but it's a statement about when Dr. Pin says alphabet, what does he mean? He means a non-empty finite set. An example would be the set containing the numbers 0 through 9. A word is a finite sequence of symbols from an alphabet. So a word over the alphabet A might be 69420. The free monoid we already covered is the set of all words from the alphabet. So for instance, with my example of A star would be the natural numbers, except that you can also have leading zeros. 1 is going to denote the empty string, as it did before in the case of the free monoid. And as I said, a language over an alphabet is any subset of the free monoid. So examples of languages over my alphabet that I gave, namely 0 through 9, would be the natural numbers, the positives, the even numbers, odd numbers, binary programs that terminate, binary programs that are written by Microsoft engineers, prime numbers, real world RSA moduli, ternary encodings and access passwords, etc. The first number or symbol in a word is called the initial. The last one is called the ending. Some consecutive symbols at the beginning that are that begin with the initial are called a prefix. And
Nice.
if it's not the entire word, then we say it's a proper prefix. You can also call it a left factor or a proper left factor. Conversely, I guess, or by corollary, I don't know. On the right, if we have something that concludes with the ending and includes, and is consecutive, we call it a postfix or right factor. And if it's not the entire word, we call it a proper postfix or proper right factor. We can also have a subword, which is a word consisting of, in order, some symbols within the broader word. So in this case, 460 is not a subword of 69420, but 640 is. This is definitely the example from Pin's book. I'm pretty sure.
For sure.
Yeah.
No Elon or anything
No,
on Twitter.
No.
Dr. Pin likes this.
Yeah,
one.
yeah. I think he endorses this. Dr. Pin, please still come to my talk, or to the event. Anyway, and if it's not the entire word, it's a proper subword. We can measure the length of a word, which is namely just the number of symbols in it. And we denote this with absolute value. So 69420 is 5 symbols. If we do a subscript with a symbol, that means we're counting the number of instances of that symbol in the word. So the subscript with 6 is going to have 1. And in this example, I've added more 6s to this number, and now it has 4 6s. And that is the meaning of that notation. We call a word multilinear if it contains less than or equal to 1 instance of every letter in the alphabet. So the empty string is multilinear. And in the case of the alphabet I presented of 0 through 9, 69420 is multilinear, but 69666 is not, because it contains multiple instances of the number 6. So if a word contains more than 1 instance of a symbol, it is not multilinear.
Can you go back 1 second? I'm sorry, maybe this is a bad question, but is there any intuition for why that name is meaningful and why we care about this fact?
I have no idea. Do any of you theory people know? I don't know.
That's fine.
I imagine it somehow relates to maybe the generalized star height problem.
Okay.
Yeah, or maybe some elaborate theorem in Pin's book, which
Sure.
I don't have on hand. But
That's fine.
Yeah.
Thank you.
Anyway, he made a point of it in his book, so I figured I should cover it, and it's an
Sure.
easy enough definition. Okay, we have the operator that we already discussed, the concatenation operator. And all it does is concatenate things. It's associative, it's non-commutative, because 69420 is very different from 42069. Its identity is 1, the empty string, and it naturally implies an exponent, right? So like 420 cubed is 420, 420, 420.
And should this have parentheses, or instead of 42000 or something, but not relevant, doesn't matter?
Oh, sure. Yeah, like parenthesis 420 end parenthesis.
Okay,
yeah,
sure.
You're right. Yeah. Yeah, because I guess technically you might interpret this as being 42000. Right. Yeah, that's a good point. And we can lift this to sets of words quite easily. So actually, any of you who know group theory have probably seen this. But basically, if you multiply one language by another, you get the list of all words that start with the word in the first language and end with the word in the second language. So 69 times 666, 314, 420, and 000 is going to contain 69, 666, 69, 314, 69, 420, and 69, 000. So each of those begins with 69 and ends with one of the words on the right. This again is associative and non-commutative, just like the one we just looked at. That was just for words. Its identity is the set containing 1 or containing the empty string. And I chose to denote that with a math Blackboard 1, but I don't really know what the standard is. I think it's actually quite interesting that its identity is the set containing 1 as opposed to just the empty set. And I don't have a good explanation for that yet, but if somebody else on this call does, feel free to share. It also clearly implies a exponent because we can multiply a set by itself.
I guess the intuition I would say is if you look at cardinalities, it might make sense. Where you could say the overall size of the set is the product of the cardinalities of the sets.
Oh, yeah, that's nice.
So if you have an
Yeah.
empty set, you'd have 0 elements.
Yeah, that makes
Maybe,
sense.
I don't know.
That's a good, I like it. I endorse it. We can do set subtraction. So, or is that what I wrote down? I don't think that this is correct. Oh no, this is correct. Yeah.
Mhm.
If I subtract 6 and 300 from 6 and 9, I'm left with only 9 because 300 was never an element of the set, but 6 was.
You
we
could
can do
read it
union.
as elements in the left-hand side that are not in the right-hand side.
Yes, correct.
It's how Python does it too, I think.
Yeah. We can do union, which is just set union. And we can do complement, which is everything in the free monoid except for the language. So for instance, you could do some pretty complicated things. Like you could say, I want to look at the complement of the language of computer programs that terminate. So that would be the language of things which, if you view them as a computer program, do not terminate, right?
Can you say that one more time, please?
Okay, if you imagine that every number can be viewed as a computer program,
Mhm.
then the complement of the set of computer programs that terminate would be the set of computer programs that don't terminate.
Okay, right. So these operations here you're saying are really nice and easy, but then this one you can use, but ends up with stuff that you can't feasibly compute potentially.
Well, you might, if you started with something you can't compute, you might end up with something you also can't compute.
Right.
Right, yeah. So in other words, there are examples that are like more interesting maybe than the ones we're looking at. That covers everything we needed to know for words and languages, I hope.
Maybe this is a good point to stop. Are there any questions at this moment? We're about halfway through and we keep cruising, but sorry to interrupt.
No, no, perfect. All right, cool. Next, we're gonna do DFAs. Okay, so Dr. Pin sort of presents DFAs a little differently from how I've seen them presented before. So I'm gonna show both presentations, I guess, in parallel. So a DFA, according to, well, actually, I'm just gonna start with an automaton, and then I'll explain how to make it finite and how to make it deterministic. So an automaton, plural being automata, an automaton, according to Dr. Pin, consists of 3 ingredients: a set, which he denotes as Q, and which we also denote as Q in, I guess, most computer science textbooks, like in Sipser, for instance, but we call it a state space. An alphabet, which he denotes as A, but I think is more classically denoted as sigma, although I've seen other things too. And what he calls an action from the set and the alphabet to the alphabet. No, sorry, from the alphabet and the set to the set, which we, I think, more commonly view as a transition relation from the state space and the alphabet to the state space. So these are equivalent notions. And I guess the point is that if you see him writing down something that looks like he's multiplying an input symbol by a state and he's getting back a state, that's equivalent to him just saying that if you applied the transition relation at that state on that symbol, you would end up in that final state. And we'll go over this again momentarily. We say that the automaton is finite if it has finitely many states. In other words, if the set, i.e. the state space, is finite. And we say it's deterministic if the action, or in other words, the transition relation, can be explained by a function. So if the relation is a function, it is deterministic. In contrast, if there is some state S and some symbol pi, such that the relation takes you from S given pi to both S1 and S2, which are different, then it would not be a function, right? So then it would not be a function, therefore not be deterministic. And we're going to show this visually in a second. I think it'll be easier to see visually. Actually, like automata kind of suck unless you draw them, in my opinion. So at the very least in my research, I always just draw pictures instead of trying to use math. And this is what an automaton looks like when you write it down. So we draw the states in little circles, and we draw the transition relation by drawing an arrow from the state to the state where it ends up, labeled by the symbol that was an input. And some of you might be wondering if you are familiar with the idea of starting in an ending state, or like a starting state and an accepting state, or something like this, where those are, and they're on the next slide. So basically, there's different definitions you can accept, but Dr. Pin does not include the initial states or the final states as part of the definition of the automaton. We're in like a realm of math where there's not like one fixed definition. So different people use different definitions. Even the same author uses different definitions. Like I've read multiple papers by Moshe Vardi, they use different definitions. So it is what it is. But we're going to have this idea of an initial state or multiple initial states and a final state or multiple final states. And we'll use it to define the language that the automaton accepts. So a path is a sequence of consecutive transitions of the automaton. It's literally a path through the graph representation of the automaton. And we call a path final if it ends in a final state. We call it initial if it starts in an initial state. We call it successful if it is both final and initial. So we say that the automaton accepts a word if that word consists of the in-order symbols on a successful path. In other words, Y would be an example of a word accepted by this automaton, because there's a successful path that goes from S2 to S1, and S2 is initial and S1 is final. But another word would be YZX, right? Because it goes S2, S1, S0, S1. And so it is, again, a successful path that ends in the final state, it begins in the initial state. And so the language accepted by the automaton consists of all the successful paths. And more specifically, we say an automaton accepts a language if and only if there exists a choice of initial states and a choice of final states for which that language is the language that is accepted by the automaton. So this is confusing because some people would include the initial states and the final states in the definition of the automaton, whereas what Dr. Pin does is he doesn't include them. He just says there must exist some choice for which it's accepted.
That's interesting. So you could use one state machine and color in different initial and final states
different languages
and have different languages.
Yes. Yeah. From Dr. Pin's perspective. Yeah.
Right.
Whereas like, for instance, in my FM research, I would consider those to be totally different machines.
Right. That is interesting.
So it's pretty common to use a calligraphic, is that the word? A fancy math cal. I only know LaTeX because I'm ignorant. It's pretty normal to use a math cal A for an automaton. I've seen this a lot in FM literature, like Moshe Vardi does it a lot. And it's also what Dr. Pin does. And as I just said, we say that an automaton A accepts the language L if and only if there exists a choice of initial states I and a choice of final states F, such that L equals all the successful paths from I to F. So it's not just contained in them, it equals them. And that's the definition that is in Dr. Pin's book. Okay, we've now covered everything we need for DFAs, and we're going to go over regular expressions and languages. Regular expressions and regular languages. Okay, so this presentation might look slightly different from what you've seen before because I'm again using Dr. Pin's presentation. So let A be a finite alphabet. We're going to define a new set rat of A star, which is the smallest subset of A star satisfying the following conditions. We'll show momentarily. And this subset, just so you know, is going to be the regular expressions over A star. First of all, it needs to contain the empty set. So the empty set is an element of the regular expressions over the free monoid of A. If a letter is in the alphabet, then the set containing that letter is in the regular expressions over A star, right? It's in rat A star. And if two sets are in rat of A star, then so are their product, their union, and the free monoid over either of them. Okay, so Dr. Pin calls these rational expressions and rational languages. I've never seen anyone else call it that. And I spoke to some PL students who also had never seen that before. But his work is translated from French. And so it might be an artifact of the translation. I don't really know. But I just want you to know when you attend Dr. Pin's talk that if he calls it rational, it's what we call regular. Okay, and that's why he writes rat of A star. So a theorem, which I'm not going to prove, but is reasonably straightforward, is that every finite language is regular. And some examples of regular languages would be, first of all, if we take the alphabet containing, or not the alphabet, but the set containing A, B, and BA, and we do the free monoid over it. So we get things like A A, B, A, B, A, B, B, A, or B, A, A, B, B, A, A, B. That would be a regular expression, also a regular language. Another would be A star, A, B, A star. So that would be all the words that consist of first a prefix from the free monoid over A, and then the characters A, B, A, and then a postfix from the free monoid over A. We could also have A, B, A star, which would be the subset of the free monoid over A, in which every word starts with the prefix A, B. And you can also have the set of words of even length. Anki, go ahead.
Yeah, given that we, you talked about regular being called as rational. Isn't the theorem in his work, every finite language is rational?
Yes, yeah.
So, if you talk about regular being called as rational, then it would be better to, from now on, talk in terms of rational.
Okay, that's a good point. You're right. So we'll just be consistent. We'll say rational.
Yep.
Yeah.
And one more comment. Here, star is talking about the free monoid, right? It's not a multiplication symbol, just for clarity.
It is the free monoid, but also the reason that they denote it that way is because it's arbitrary multiplication with itself.
Sure.
Right.
Okay. But I should read this as A star, not A star ABA.
Yeah.
Okay.
Correct. Yeah.
Okay.
Absolutely. Yeah. And I guess like I could make it like an exponent. Like
No, you're fine.
Yeah.
You're fine. Just wanted to.
Yeah. Okay. So so specifically, I want to be clear that A star, ABA, A star is the regular expression or the rational expression defining the regular language, or as Anki points out, the rational language, which consists of first a prefix from the free monoid over A, so some symbols A naught through AK drawn from A, and then the letters ABA, and then a postfix from the free monoid over A. And the prefix and or postfix might be empty because the free monoid contains an empty string, which we call 1. So that's sort of the meaning of that regular expression or that rational expression. So some things are not regular or are not rational. So examples would be the set of all prime numbers, the set of all terminating programs, the set of all pairs of programs that do the same thing, however you like to define that, as long as it's a reasonable definition, or the set of all strings consisting of opening and closed parentheses, in which every open parenthesis is closed and vice versa. And that last one is an interesting proof we're not going to do, but it is interesting. And I think it's actually an exercise in Sipser's book, but it's kind of cool. That suffices to explain what we need to cover for regular, AKA rational expressions and languages. Now we're going to do metric spaces. This is like completely unrelated to everything else we discussed today, but I was asked to cover it, so we're covering it. So let's imagine that X is a set containing some items. It might have infinitely many that are, it could have uncountably infinitely many. It might have nothing, but whatever, it's a set. And let's say that D is a function which takes 2 inputs from the set and returns a real number, and it satisfies the following conditions. First of all, D of X, Y is 0 if and only if X equals Y. So D is going to measure a kind of notion of distance, and intuitively the distance from myself to myself is 0. But if the distance from myself to something is 0, that thing must be me. So it's an if and only if. Second, the distance from me to Jacob is the same as the distance from Jacob to me. So we have a symmetric property. And third, we have something called the triangle inequality, which says that the distance from me to Jacob plus the distance from Jacob to Katie is greater than or equal to the distance from me to Katie. So I want to be clear, this doesn't imply like the Pythagorean theorem or anything like that. It's like it's a weaker condition, but it just says that it's better to go in air quotes straight than to take a meandering route, right?
And congratulations, you've now learned the one trick you need to pass real analysis.
Yeah, basically. Well, one of two. You need the epsilon delta, but yeah. So if it satisfies these properties, we call it a metric on X, and we call the pair between X and D a metric space. So let's say that we draw a sequence through the space. Like in this case, I covered up the letters, so it's kind of ugly, but I like started at the bottom and I went left and then I went right and then up and then left and then down and then left and then down, right? I can use my distance function to measure the distance of each segment in my sequence. Maybe the sequence is infinite, right? I mean, this is sort of a boring example because I made it stay at K forever, but we'll show some more interesting examples shortly. But you could have an infinite sequence. If the infinite is sequence, and if the distances of the line segments converge to 0, then we call it Cauchy, or a Cauchy sequence. So here's some examples. One would be 1, 1/2, 1/3, 1/4, 1/5, 1/6, etc., which is a Cauchy sequence because the distance between each pair of items is smaller than the previous one, right? And it converges to 0. It's not just smaller, it's smaller in a way where the smallness converges to 0. In other words, the limit as t goes to infinity of the distance between the t item and the t plus 1 item is 0. Another example would be the sequence of vectors. It starts with 10, 10, 10, and then has 10, 1, 1, and then 10, 0, 1, 0, sorry, 0.1, 0.1, and then 10, 0.001, 10, 0.001. If we take the Pythagorean, or sorry, if we take the, what's it called? The Euclidean distance between these things, it's a number that is going to approach 0. Another example would be the digits of pi. So if we take the first digit of pi, and then the first 2 digits of pi, and then the first 3 digits of pi, etc., the consecutive distance between each item in this sequence is like on the order of 1/10 of the distance between the previous items. So I want to make this observation that a Cauchy sequence might converge outside of the space. So like the sequence that contains 3 and 3.1 and 3.14, etc., it contains only elements from the rational numbers, yet it converges to an irrational number, which is an interesting point. So if the space has the property that all the Cauchy sequences converge inside the space, none of them exit the space, we call it complete. So like the rational numbers are not complete because, for example, the sequence that converges to pi converges outside of the rational numbers. Right, so they're not complete.
So in this table, which ones are complete and which are not?
Well, I mean, you could imagine any of these being a sequence within the irrational numbers, which are, I guess, actually not complete either if you use certain metrics. But
these first two,
or I'm sorry, no,
probably.
Yeah, I think the irrational numbers are complete. The sequence is not intrinsically complete or incomplete. It depends on what space you put it in.
Oh, I see. Okay, so it depends on the space.
Yeah.
All right.
Right.
Yeah.
Actually, it will depend on what x you are using. For example, in the last example, if x is rationals, then it is not complete because pi is not in rationals.
Yeah, exactly. That's what I meant by what x you use, right? Because I called it here.
Because matrix space is x comma d, so depends on x.
Oh, good point. Good point. Yeah.
Okay, so we need to track what the sequence is doing and what the space is.
Right.
Have a measure of completeness or not. You can't just look at one individually.
Exactly. And the space consists of both the set and the definition of distance, because it'll converge to a different thing depending on how you measure distance.
Okay.
Right. And a lot of, I'll just tell you, like, I think it might be the case that everybody on this call has done real analysis. I don't know, but for those of you who maybe haven't, or if people watch this on YouTube afterward and have it, you should just know that there's other ways of measuring distance besides the Euclidean distance that you're accustomed to, which behave in ways that are really counterintuitive. And like, that's one of the things that makes it hard.
And one really nice example of that is taxi cab versus crow flying. Thanks, Katie. So for example, if you're driving through a city and you're a taxi driver, you don't care what the fastest path is in RN. You want to know what street you're on, but the crow doesn't care at all.
Yeah,
and they
because
can
the
just
taxi
fly in
cab,
the right direction.
it can't like drive through buildings.
Yeah, there are many other more abstract examples, but that's the next concrete one.
Yeah, actually, there's a really cool book called Counterexamples in Topology, which I think everyone should read because it's fucking sick. And it's only like 80 pages, it's tiny, and it's just full of stuff like this. It's super cool. Okay, so it might go outside. Okay, so let's say that we have a metric space and it's within some bigger space, right? Like the rationals are a subset of the real numbers, for instance. We're going to say that the smaller one is dense in the bigger one if everything in the smaller space, every sequence in the smaller space, either converges within the smaller space or converges to point in, sorry, let me rephrase this. I screwed this up. We say that X is dense in Z if everything in Z is either in X or is a limit point of a sequence in X. Sorry, yeah. So basically like everything in the bigger space is either part of the smaller one or there's some sequence in the smaller one that converges to it.
Okay, and we haven't used the term limit point. In my head, can I think of that as the place a sequence is converging to?
Yes, yeah,
Okay.
absolutely, yeah. Okay, so that's what dense means. Okay, so I'm sorry, we don't need dense for the next question, but it is a word that Dr. Pin wants us to cover. It's also like a commonly used word, so we should cover it. Okay, so a question, let's go back to this idea of completeness. What if we have a space that's not complete with our definition? So we might like to know, like, what is the smallest number of modifications we can do to make it complete, right? And that's what a completion is. And momentarily, I'll show you how to make a completion of a space. I'm not going to justify it. I'm just going to give it to you. But it's pretty simple, actually. So, I mean, the justification is not that simple, but the technique is simple. Okay, so if we have a metric space, how can we fill in the holes to make it complete? So let X be a space with the metric D. So XD is a metric space. For each pair of Cauchy sequences, for instance, let Z and V be Cauchy sequences, I'm going to let capital D be a function that returns the limit of the distance between their nth elements as n goes to infinity. So it's essentially giving us a notion of the distance between their limit points, or between where they converge.
This is like a sequence of limit points of the difference between these limit points. Okay.
Yeah. I want to use capital C of X to be the set of Cauchy sequences in our original space, like the ones I just discussed. Now, immediately, your brain should be going, oh, is D a metric on capital C? And the answer is no, because there might be two different non-equal sequences that converge to the same place. And those would have a quote unquote distance of 0, despite being different, which would contradict our property we require that the distance from me to me is 0 and the distance from me to anybody else is more than 0. Does that make sense?
Say that one more time. Even the same thing.
Sure.
One more time.
So you might be wondering if capital D is a metric. And the answer is no, because capital D will give 0 as a result when you give it two sequences that are different yet converge to the same place.
Okay.
But a metric can only give you 0 if and only if the inputs are the same thing or identical.
Okay. So I'm just going to spitball an example. You can let me know if it's a good one or if there's something wrong with it.
Yeah.
So let's say we have a set that has all rational numbers under 1.
Okay.
And our sequence in that set is it starts with, or let's say 1 and under. It starts with 1 and divides by 2 every time.
Yeah.
So that's a sequence that goes to 0
Yeah.
and the distances get smaller.
Yeah.
Now let's say there's another sequence that starts with 2 and divides by 1/2 every time.
Multiplies by 1/2.
Or multiplies by 1/2. So it's converging the same way. It's the same sequence, but it starts 1 earlier and that one number is outside.
Yeah, your example works, except that you messed up with the definition of the space. There's 1 and under, and then you started with 2.
Oh, in a different space? Okay.
So they have to be in the same space.
Same
right?
space. Okay,
yeah.
So that's a problem with it.
Yeah,
so
but a better example would be like the one that divides by 2 every time versus the one that divides by 7 every time.
Okay.
Right? Those are two different sequences, but they both converge to 0.
They both go to 0,
and
the distance between the two
approaches 0.
is going to 0.
Yeah, exactly.
Okay.
So they would get a value of 0 from capital D, but they're different, and therefore capital D is not a metric. And now we're going to force capital D to be a metric. So I'll show you how we do that. So I'm going to define an equivalence relation that says two things are equivalent if capital D says that they are the same, because they're close, right? So in other words, two sequences are equivalent if they both go to the same place. No matter where they start, they can start wherever the fuck they want. But if they end up in the same place, they're equivalent. And we're going to use this notation with brackets to refer to the equivalence class of a sequence. So the equivalence class of the sequence D, in this case, if D says that Z and V are 0, then the equivalence class of the sequence Z is all of the things that converge to the same place as Z, which is also, in this case, the same as the equivalence class of the sequence V, because I just said that their distance is 0. So the equivalence class of a sequence is going to be the set of all sequences that go to the same place. I'm going to put brackets around C of X to denote the set that is just the set of equivalence classes, the sequences in X. And I'm going to put brackets around capital D to mean the distance function, but defined using sequences. And an undergraduate level proof you can do in your free time if you want to, is you can prove that this is well defined, which it is, but I'm not going to prove it today. So in other words, you can prove to yourself that it doesn't matter what choice I use to represent the equivalence class Z in this case. Anything within that equivalence class you could use in the distance function on the right, and you get the same result, right?
Great.
Okay. Now, this is going to be a metric space. And in particular, it's the completion of x comma d. And there's some like formal guarantee about it being like the minimal, I don't know, modification or something, but I don't know what it is. So I'm not gonna get into it. But it's like, it is the simplest way to take something that's not complete and make it complete.
Okay, so why is it a little x there because of a typo? Is it supposed to be C of a capital X?
Yeah, that
or-
should be capital. That's a typo.
Okay,
Yeah.
so you're saying we started with x comma d.
Yeah.
And we want to be able to look at the difference between sequences, but that would not necessarily stay inside of our metric space. So we do this completion where we tweak our distance function a little bit,
Mhm.
and now we have what we want.
I'd word it a little bit differently. We start
Okay.
with x comma d, and we wanted all the sequences in the space to end up within the space.
Mhm.
And so we did a construction where we lifted ourselves to this, instead of x, we're in the space of sequences over x, and instead of d, we have a way to measure the difference between two sequences, which is the difference between their limit points. But it didn't satisfy one of the properties of distance function, which was this property that it assigns 0 if and only if it's the same thing. So we just moduloed out by the problem. Like we took the things that are annoying and we said modulo that,
Okay,
and then we ended up with a space that worked as a
Okay.
metric space.
so we keep the properties we wanted from before,
Yeah.
and lift it up a little bit, and now we get our metric space.
Exactly.
Great.
Yeah.
Thank you, Max.
And I'm not going to prove it, but you're welcome to. I've actually looked at the proof. It's not too hard. It's like, it's an undergraduate exercise that I've seen in curricula from a number of schools. Okay, so some examples of completions. One would be that a completion of the rationals would be the real numbers when you use Euclidean distance. Euclidean distance is not the only distance you can use. It turns out that every completion of the rational numbers is either the real numbers or a p-adic number space. If you're curious about p-adic number spaces, don't fret, because my dad and I interviewed Bryden Case for like 3 hours on the topic at the University of Arizona, and you can go listen to it. And we spent 30 minutes on the number 0, and my sister was driving a car while I played the podcast, which almost crashed from boredom. But if you're into that type of thing, you might enjoy it. Now we have only one thing left. It's like literally one slide. Okay, Dr. Pin denotes functions a little differently from how I do normally, but it's actually pretty cool. And I'm told that a number of people do this. Basically, all right, do we have a question in the chat? Oh, Daniel has to go. That's fine.
Thanks for coming.
Yeah, thanks, Daniel. Okay, let's say you have two functions, f and g. F goes from x to y, and g goes from y to z. Okay, so then the composition of g with f goes from x to z. Right, we all know this. You can like line it up on a piece of paper. It makes sense. But that's kind of wacky, right? Because g goes from y to z and f goes from x to y. So like geometrically, it kind of looks shitty because you're like, well, I started here in y, I went to the right, ended up in z, and then wait, what happened? I'm somehow in x. Like it doesn't really line up visually. So there's a way we can write it where it's going to visually line up, which is sick. Okay, so that's kind of lame because the signatures don't line up. If you don't know what I mean, don't worry, you'll see in a second.
So this is not postfix, what you showed just now.
Yeah, that's like normal notation.
Okay.
Now here's postfix notation. What if we could write x f g instead of g composed with f of x? So x f g would be like x walks through the door named f, and then it walks through the door named g.
I like that. So you're thinking about passing x through all these functions.
Exactly.
Nice.
And if you do that, it's really cool because f goes from x to y and g goes from y to z. And so when you look at them from left to right, it's just x to z. Right.
You can put the x, replace the x with a 1 to x arrow, so that you see what the type of x is 1 to x.
Can you explain that again?
Instead of saying the element x in the lower line, you could put
Mhm.
parentheses 1 goes to x, because that's the type of little x, is a function that goes from the unit to capital X.
Which line are you talking about? The very bottom one with the really big arrow to z, or the one right above that, or?
The very bottom line. So instead of a lowercase little x, you could put a 1 to x. So you're viewing the little x as a function that starts from the unit.
Interesting.
Okay, I don't think I understand, but not through a fault of
but-
yours.
But variables are nullity functions. Like they shouldn't be taking 1 as input. They should just
You can
produce.
still think of it
X.
as a function that takes the one element set and just puts it as at the element little x of big X.
Daniel, I think I'm sorry, you're not Daniel, but I can't see your name because I have my window closed. Who am I talking to?
Amar.
Amar. Oh, okay. Amar, I'm sorry that I didn't recognize your voice. I understand what you're saying. You're making this point that you can view everything as a function, right? This is like a lambda calculus-y thing. Is that right?
Yeah. Yep.
Yeah. Okay, I agree. So in other words, if I'm understanding you correctly, your point is that if we want to live in like fancy lambda calculus land and pretend that I paid more attention to Pierce than I actually did when I took IPPL, then I would fully understand in this hypothetical world that like we can live in a world where everything's a function and there's you never like boil down to a raw variable or something like that, right?
And all our variables are, for however many types of variables we have, there is a function that says one goes to this thing.
Yeah. Okay.
Is that right?
Exactly.
Okay.
Yeah,
I don't mean in a pejorative sense. I just mean like I'm bad at PL. So
Yeah,
I'm like
can you
catching up
please
with
explain
you.
why you like this? Because it makes sense, but I don't necessarily understand the practical implications of thinking about it in this
Just
way.
make the last line prettier than, so now it's all capital letters.
Okay.
Oh, cool.
Gotcha.
Okay, nice.
Much prettier.
Yeah, there you go. Max anticipated this comment from you.
Awesome. Thanks, Amar. Okay, that's it. And I want to thank Chang, Artem, Lucy, and Akshar for all giving feedback. And I think other people might have as well. And any thing that was good about this presentation is due to them, and any mistakes are entirely due to me. And I doubt either of you have questions, but if you do, feel free to ask. Awesome. Okay, so tomorrow,
Could you repeat what the talk is going to be about?
Yes. So, okay, so it's really.
Should we stop the recording or?
I think it's fine. Okay. So there's really two events. So tomorrow, Chang is going to give a talk on Kleene algebra, and it doesn't require everything that I covered today, but he did say that like this material would be helpful for understanding his talk. And I think that talk's gonna be kind of like monoids and formal languages, but to be honest, I know nothing about Kleene algebra, but I will tomorrow after his talk. And then on Friday, Dr. Pin is going to present the Generalized Star Height Problem, which I don't know much about, but he describes as an open problem in sort of formal language theory and automata theory. And I think it's been an open problem being investigated for a few decades, if I remember correctly. He has some write-ups online about like research that's made progress on the problem, but it's my understanding from what he's told me, if what I've read, is that it's one of these problems that is sort of relatively easy to understand, but nobody can figure out. And it involves automata and formal languages. And Dr. Pin is quite famous in formal language theory and wrote one of the kind of seminal books on the topic of varieties of formal languages. Although I'll tell you right now that some people disagree with his definition of variety. And if you want to hear about that, you should ask Matthias because he has his own opinions about that definition. Regardless, it's a good book. I like it. And I think the talk will be quite good. So, and he's really a mathematician as opposed to, I guess, a computer scientist. So it's like a blurry line, but I think he falls on the mathematician side of it. So that's going to be on Friday next week around noon. And if you can only attend one of the talks, I would say attend Dr. Pin's talk because he's a difficult to get guest, whereas Chang is a buddy of ours and comes to a lot of our events. And I'm sure you could talk to him in the future or attend one of his events at BU. But if you can attend both, I think they'll both be pretty cool. So I'm going to post this video on YouTube. There's also going to be an audio version online. And when I send out emails to people inviting them to come to Dr. Pin's talk later this week, I'll include links to the video and audio so that they can review if, I think like, honestly, I don't think that it'll be that mathematically intimidating, but I think some people worry when they see like, oh, famous mathematician coming to give a talk. And so it might be nice for people to know that there exists a resource. Yeah.
Thanks, Max, for setting it up. The slides were awesome.
I did my best.
I don't know how long it took you to draw the squiggles in of the spaces, but I loved it.
Well, I did get the entire like PL group at Northeastern to give feedback, which was productive. Okay, any other questions or should we call it a day? Awesome. Okay, thanks for coming, guys.
Thanks, guys.
Thank you.
Adios.
Bye.
Okay, bye.